All right, today we're going to do something pretty cool. We're jumping back in time more than 2,000 years to see how one of the greatest minds in history measured our entire planet. And get this, he did it with little more than a stick, a well, and a shadow. Sounds wild, right? Let's dive in.
I mean, seriously, think about that for a second. How on earth do you measure a planet, the very one you're standing on, with no satellites, no modern gadgets, nothing but your own brain? It sounds completely impossible. But you know what? It's not.
So, who's the guy who pulled this off? This is Eratosthenes, an absolute genius. He was a Greek scholar and the head librarian at the legendary Library of Alexandria. He was a master of many things, but we remember him today as the father of geography for one truly incredible reason. He was the first person to accurately calculate the circumference of the Earth.
So what was his secret? You might be thinking it was some, lost ancient technology or a super complex formula. Nope, it all came down to something we see every single day and probably never think twice about: a shadow. Or more accurately, the lack of a shadow.
Eratosthenes' big idea all started with this really interesting fact he'd heard. He was told that way down south, in a city called Syene, something amazing happened on the summer solstice. Right at high noon, the sun's rays would shine straight down to the bottom of a deep well, leaving no shadow at all. But back where he was, in Alexandria, hundreds of kilometers to the north, he looked outside at that exact same time and saw that a tall pillar was casting a very obvious shadow.
So, why the difference? That was the big question. If the Earth were flat, the sun's rays would hit both cities at the exact same angle. That means both places should have been shadowless. The only possible way for a shadow to appear in one city, but not the other, is if the surface of the Earth itself is curved. That one simple observation led him to a massive conclusion. The planet beneath his feet was a sphere.
Now, to make all his math work out, Eratosthenes had to make one crucial but very smart assumption. He figured that the sun is so incredibly far away from us that by the time its rays get to Earth, they're essentially traveling as parallel lines. This seems like a small detail, but trust me, this simple idea was the key that unlocked the entire puzzle.
So here's how we put it all together. Step 1. Observe that there's a difference in the shadows. Check. Step 2. Measure the angle of the shadow in Alexandria. He figured out it was about 7.12 degrees, which is just about 1/50th of a full circle. Step 3. Find out the distance between the two cities. And that's it. With just those 3 pieces of information, he used some basic geometry to calculate the size of the entire planet, an absolutely masterful piece of thinking.
And all of this got us thinking, could we recreate his experiment today, but with modern tools? So that's exactly what we did. Let's see if we can be Eratosthenes' digital apprentice.
The tool we're going to use for this is really cool. It's an open source software called Stellarium, and it's basically a virtual planetarium for your computer. It lets you simulate the sky from anywhere on Earth at any point in time. So of course, we fired it up and dialed the clock way back to the summer solstice in the year 240 BC.
Okay, first things first, we had to set our locations. Just like Eratosthenes, we needed 2 observation posts, Alexandria and Syene, which is near the modern city of Aswan. Stellarium lets us pinpoint these exact ancient spots. Then, at local noon on that ancient day, we measured the sun's altitude, that's just its angle above the horizon, in both of our virtual cities. We grabbed the precise angles the software gave us to find the difference, basically doing exactly what he did, but, with a keyboard and mouse.
All right, this is the moment of truth. We've got Aristotlenes' original calculation, we've got our modern recreation using Stellarium, and we have the actual known value of the Earth's circumference. So, how do they all compare?
Well, the results are pretty fascinating. The actual circumference is about 40,075 kilometers. Our Stellarium recreation landed at 46,360 kilometers, but Aristophanes, over 2,000 years ago, calculated it to be 40,700 kilometers. I mean, that is just astonishingly close.
Just how close? His calculation had an error of only 1.56%. Think about that for a minute. With absolutely nothing but his observations, his reason, and some very basic tools, he was almost perfectly correct. It's a true testament to the power of the scientific method.
And our modern attempt?
Well, even with powerful software, we had a much bigger error of nearly 16%. Now, this doesn't mean the software is bad at all. It just highlights how many tiny variables can affect the outcome. And honestly, it makes Eratosthenes' achievement even more incredible.
So, okay, this is a great story. But why does it still matter today? Well, because the kind of thinking Eratosthenes pioneered, understanding our position by observing the heavens, is the very foundation of modern astronomy. This way of thinking leads directly to how we map the sky today. There are really two main systems. The first is the azimuthal system, which is your personal, local view, what you see relative to your own horizon. But then there's the equatorial system, and that's like a universal map, a fixed GPS grid for the stars that works for everyone, everywhere on Earth.
And here you can really see the limitation of a local-only view. We're looking at the sky from two different cities at the exact same time. In the azimuthal system, the coordinates for the moon and planets are different, because everything is just relative to the observer on the ground.
But switch over to the equatorial system, and suddenly the coordinates are identical. It's a universal grid. This is what allows astronomers all over the globe to collaborate, to point their telescopes at the exact same spot in the cosmos, and it's a direct intellectual descendant of Eratosthenes' realization that we need a framework that's bigger than just our local viewpoint.
And really, that's what this is all about. By recreating these ancient experiments, we're not just looking back at history, we're connecting the past with the present, and continuing to learn more and more about the cosmos.
The ultimate takeaway is that the power of simple observation and a curious mind can truly change the world. It really makes you wonder, doesn't it? What seemingly small detail today might just hold the key to our next great discovery? Thanks for tuning in.